Welcome to our MAE 3340 instrumentation project. We are Group 8, and our project was to examine 3D printing infills at a 15% infill. The idea was to examine patterns from a pool of patterns to determine which is the strongest in a given compressive test.
Our target customer is hobbyists, so people that like to do a lot of 3D printing on their own time, and rapid prototyping applications by engineers to help them in their respective fields.
Our approach is to run compressive tests on a pool of samples of 3D printed cubes using this Tinius-Olson compressive tester.
And using 95% confidence, we used our data and calculated a 5.1 uncertainty value.
When 3D printing, the inside of parts is often hollowed out to significantly reduce weight and material consumption. An internal structure is then added to these hollow areas to optimize the strength of the parts. So, what infill pattern is best suited for a compressive load? The answer will help hobbyists, prototypers, and engineers decide on one of the many options for infill patterns. Our final results will show the ultimate strength of each pattern, all at a 15% density, and compare that to a control group of solid cubes. Customers would like to see the modulus of elasticity as well for design reasons. We will only present a winner if, at a 95% confidence, it can be shown to be stronger than others. Its ultimate stress interval should be larger than the other mean ultimate stresses. This requirement means that our data must show a significant benefit for a specific infill pattern over others.
To compare internal structure options, we printed cubes using 8 15% infill patterns. We used trihex, octet, lines, grid, cubic, zigzag, lightning, and gyroid. Each provided a different internal load path, giving us multiple design alternatives. A 100% infill cube served as our baseline for maximum strength, with additional reasoning included in our design decisions appendix. We did our testing on a Tinius-Olson machine because our cubes were designed to be loaded in compression, and the machine provides controlled force and accurate measurements. We assumed the PLA and printing process produced consistent material behavior, and that any variation from printing or alignment affected all designs similarly, giving fair comparison. These assumptions were valid because all parts were printed using the same filament, settings, and orientation. To reduce risk and keep the focus on infill geometry, we measured each cube, aligned specimens the same way, used identical machine settings, and stopped tests at the same plateau region. This reduced variability from printing, operator influence, or machine setup, giving us proof the method could reveal differences caused by infill geometry. Our test procedure followed a repeatable process, measuring cubes with calipers, centering them under the plate, and running the machine at a controlled loading rate to avoid force spikes. Testing continued until visible deformation and plateau, ensuring each sample experienced its complete response to compression. Stress strain curves were saved for all 34 samples per infill for later comparison, demonstrating correct use of the equipment. Even with these controls, some uncertainty remained. Size variation affected stress calculations, strain reading noise affected modulus estimates, and internal voids or placement differences introduced variation. These weaknesses could not be eliminated entirely, but this shows how it can affect the data.
A common rule of thumb for 3D printing is that the gyroid infill pattern is the strongest, which was proven wrong. The testing for our 100% infill control samples also showed that the technical data sheet for PLA, obtained from Ziltech Engineering, the company where the filament was sourced from, indicated that our values for both Young's modulus and ultimate strength were higher than what was given. Our results showed that the trihexagon infill pattern was the strongest in compression, with an ultimate stress of 14.45 megapascals along with an uncertainty band of 0.543 megapascals at 95% confidence. The experiment operation required that each sample was aligned in the center of the tensile tester and not aligned with one of the holes on the aluminum compression block. However, early testing showed that minor variations in where the sample was positioned showed a negligible impact on the results of the data, since the aluminum was much less likely to deform under the same load applied to each sample. A notable difference of our results in theory was the variance of data between our control sample and the manufacturer's data. The explanation for this is that Ziltech's data was gathered from samples in tension due to the ISO 527 test, rather than in compression such as we did. A major weakness of our experiment is that 3D printers can produce defects in the print itself, including layer shifting, bed warping, and/or surface defects as seen in the image above. This leads to forces accumulating in these defects, which can lead to premature failure. The 3D printer was calibrated prior to producing the samples to attempt to minimize as many of these defects as possible. The histogram for the ultimate stress of the trihexagon infill pattern indicates that the data distribution can be reasonably approximated as Gaussian. This shows that no apparent outliers or unexpected jumps in data were found, leading to the conclusion that the calculated average ultimate stress is sound. The uncertainties included the bias uncertainty from the calipers and the precision uncertainty from the tensile tester. Both of these combined produced a total minimal uncertainty of 5.1% at 95% confidence. Due to the application towards hobbyists and prototype engineering, we felt that this is a justifiable number.
Comparing our data to the requirements and constraints set by our control criteria, we found that our best result was with the trihex infill pattern and with an average ultimate stress of 14.45 megapascals, a modulus of elasticity of 868.43 megapascals compared to the control test with 100% infill with 80.84 megapascals for the ultimate stress and with a modulus of elasticity of 6,345.64 megapascals, or roughly 18% of the ultimate stress and 14% of the modulus of elasticity, respectively. This is the best infill pattern to use in compressive purposes, being the trihex pattern, simply because it had the best results of all the samples that we tested. For our uncertainty, we did a summation of our uncertainty using our area via calipers and our uncertainty in the stress, ultimate stress measured by the strain gauge tester, which you can see here, using the uncertainty given on the back of the calipers being 0.1 millimeters and the uncertainty in the strain gauge being a 100 newtons, or about 0.2% of its ultimate readings. And some of the suggestions for the future is possibly not enough unknowns to meet the equation criteria. It was pretty easy. We measured our samples and got our data, as well as possibly not enough samples. We had a smaller population sample size. For the design appendix, two alternatives to our design would possibly be different structural designs, such as an I-beam or something of that idea that relies more on structural support instead of just a cube. So it's more emphasis on the actual infill design, as well as possibly a more fixed position to test our samples during testing. Some of the strengths and weaknesses of our design were it was simple, repeatable, and easily measured, and some of the weaknesses were non-uniform printing, if that were an issue, and noise in the strain gauge. One of the decisions for our design was the simplicity and the assumption that our uncertainty and noise in the strain gauge was not enough to matter in the end. We assumed a uniform shape throughout, as well as the force applied to the samples being uniform, and that the strain gauge had an uncertainty of 0.02%. And in order to minimize risk, we always tried to place the cube on the same face and same spot during testing.
To go into more detail about our uncertainty analysis, the error sources that we identified included the size of the cubes, imperfections in the plastic or print, layer errors, error from the strain gauge, and human error from caliper measuring. For each sample, we ran compression tests on 30 specimens of the same infill pattern. This allowed us to use sample statistics without needing the student's T correction. For a confidence of 95%, we used Z equals 1.96. Another benefit of these sample statistics is that a few error sources are subsequently included in our resulting data. The error source that is not included in the variation is the cross-sectional area of each cube, which is used to calculate the ultimate stress from the maximum force on each cube. When propagating the area variation through the stress equation, we find that the uncertainty increases by a noticeable but small amount, since the variation in the readings was higher than the caliper's precision. From our initial requirements, the null hypothesis would be that all of our samples fall within each other's strength ranges. This would mean that the infill pattern does not affect strength. Instead, the trihex pattern was shown to be stronger in comparison than any others. In fact, its lower uncertainty bound is higher than the higher bounds of all the other patterns. This graph shows the expected ranges for each pattern as a percentage of a fully solid part. Our theoretical uncertainty, which would mainly come from the precision of the strain gauge and the accuracy of our calipers, was found to be around 5.1% based on the stress-force equation and our propagations. Most samples had a final uncertainty of roughly 2%, meaning that we were able to narrow the interval with our large sample sizes.